This is IMO 1986, question number 1. The problem wanted to show that within the set of 4 different integers, 2, 5, 13, and d, we can always pick 2 integers within the set, say a and b, with a times b minus 1 not a perfect square. Our first observation is this. By choosing any two of 2, 5, and 13, we multiply them together and minus 1. We always get a perfect square. So, the only possibility is we pick d as one of the two a or b. 2d minus 1, 5d minus 1, and 13d minus 1 should not be perfect squares. We prove this by reductio ad absurdum. Suppose this is not the case, and 2d minus 1 is a perfect square. We call it x squared. 5d minus 1 is a perfect square. We call it y squared. 13d minus 1 is also a perfect square. We call it z squared. If this is the case, then x must be an odd number. We call it 2n minus 1. So, x squared, which is 2d minus 1, equals to bracket 2n minus 1 close bracket and then square, which is 4n squared minus 4n plus 1. So, d, which is 2n squared minus 2n plus 1, is also an odd number. We call this equation number 4. We put equation 4 and 2 and 3 together. We see that y and z would be even numbers. So we can write y equals to 2p and z equals to 2q. From equation 3 minus equation 2, we get x times d, which is z squared minus y squared, equals to 4 times q squared minus 4 times p squared. So, q squared minus p squared, which equals to 2d, is an even number. This could only be the case if both p and q are even numbers, or both p and q are odd numbers. If this is so, then p minus q and p plus q must both be even numbers, and we call p minus q as 2h, p plus q as 2k. So the consequence is that 2d equals to 4 times h times k, which is a multiple of 4. And this says that d equals to 2 times h times k is also an even number, which contradicts with our equation number 4. So 1 is not valid, and 2d minus 1 is not a perfect square. Now, this is the result. We can always pick a equals to 2 and b equals to d, with ab minus 1 not a perfect square.